Hey everyone, welcome to Think to Learn. Please subscribe to my channel and hit that bell button to get all the notifications about my latest video that you will really like. So what I'm here to talk about today is the standard model of particle physics. We are humans, and why is that so and why different from others is that because we ask questions. Like everything, why is it everything like gas, liquid or solid, etc.? It all leads to one fundamental question that what are we made up of? And from ancient time there were many theories about it. Dalton, a great scientist, organized them into his own theory, Dalton's atomic theory, which was a great success. But for every theory there are drawbacks, and there were many drawbacks. So he could not tell what was there inside the atom. So then there came J. Thomson's atomic model and then Rutherford's atomic model, which stated that there was a nucleus around which electrons were revolving, and proton has the nucleus consisted of proton and neutron. Neutron has no charge, proton has charge of +1 and electron of -1. We consider it to be as a unit charge. So, but it had its own drawbacks. Then came a revolutionary idea from Niels Bohr, Bohr's quantum model or Bohr's atomic model. He stated that there were fixed shells in which the electron revolved, and he quantized the radius and the energy of the orbits, which means to say that we can calculate the energy and radius of the orbit through formulas and equations that maybe not in this video, but I will include it in further videos. And there was improvement by Sommerfeld in that model. But what I'm here to talk about today is between 1940 and 1960 there were thousands of particles discovered in the LHC, Large Hadron Collider, which is a particle accelerator located at Switzerland. And then it was a chaos because there were many particles discovered and no one was there to unify them. So then there came the standard model of particle physics. And one more question was there, that there were fundamental forces. Now, who were responsible for that? What are fundamental forces? All the forces are just dependent on these four forces, namely strong nuclear, weak nuclear, gravitational, electromagnetic. All for other forces are just form of these. Like tension is a tension force that we see in the rope is a form of electromagnetic force, and friction force, etc., etc. These are dependent on fundamental forces. So this is a original model of an atom that you can, old model of an atom that you can see in your textbooks, but this is what is a standard model. Don't be scared, you just need to get the intuition. It's really easy. So what this model said was that all the matter in the universe was made up of 17 fundamental particles. These 12 were fermions that make up the matter. These 4 were responsible for the fundamental forces as stated before, and this one was a little tricky one and a little different one, also known as God particle, and this was scalar boson. So let's start with quarks. Fermions are consisted of quarks and leptons. First let's go to the quarks, one in the purple. So there are 6 types of quarks: up, down, strange, charm, top and bottom. Nothing related to the names, but they were named in this way. So they are crazy particles because they move nearly at the speed of light inside the proton and neutron, and they make the proton and neutron. So they have partial charge. Partial charge. Like up quark has 2/3 charge and a spin of 1/2. So what does spin mean? Spin means moving around its own axis, rotating about its own axis. And there are spin numbers given, like quarks and leptons. Like the fermions have 1/2 spin. These all have 1 spin, and Higgs boson doesn't have a spin. It's 0 spin. It doesn't rotate. And we can calculate the spin number by Schrodinger's equation that you can learn in a quantum physics class in your PhD. But maybe I will include in some other video. So see, up quark, charm quark and top quark. These all have the same charge and spin. So what does help us to differentiate them? How does we know that this is a top quark and this is up quark? Another property came out that we introduced was color charge. It was not related to the color, but yeah, it was color charge. We can study them under quantum chromodynamics. So that make them different. There was a different color associated with every quark. So then these 3 have the same charge and spin, -1/3 and 1/2, down, strange and bottom. So for example, the proton consists of two up quarks and one down quark, and that also fits the maths. See, 2 by 3, that we double it, we call 4 by 3 minus 1 by 3, that will give 1. So yeah, we know that proton has a charge of plus 1. Similarly, neutron is made up of two down quarks and one up quarks, like minus 1 by 3, and we double it, minus 2 by 3 plus 2 by 3, that will give a net 0, and we know that neutron has a 0 charge. So we can say that the neutrons and protons, commonly called as baryons, they are all made up of quarks in different combinations. And then came leptons. One of them you recognize as electron. Electron you are very familiar with. Muon and tau are just like big brothers of electron. They are just a bigger version. They have the same spin and charge, but they are just bigger versions of that. Actually, these three are the ones that make up the proton, neutron, and this is the electron. These all are just seen in the particle accelerators at high energy levels, so you cannot see them very easily. But these three are just make the ordinary matter. So then there came neutrino. They are called the nature's identity thieves. They were discovered due to there was a problem in mass conservation, so they were discovered. We can see them in a beta decay. Beta decay is when a neutron disappears and a proton and an electron and a neutrino is released. So that's why they were discovered. And when an electron neutrino is released, so respectively they were released in their respective decays. So fermions are done. Then we come with the gauge boson. Gauge bosons are called so because they have a spin. They move with a spin of +1, and these are all the bosons. Gluon is responsible for strong nuclear force. Strong nuclear force exists between the proton and neutron and held the matter together. This is the strongest force. Photon exists between electromagnetic force. We can study them under quantum electrodynamics. Then comes, it is also a strong force, stronger than second strongest. Then there come W and Z bosons. These two bosons are responsible for weak nuclear force that we can see in the beta decay during when neutrino was released. So this is comparatively a weaker force, but still stronger than the gravitational force, which is the weakest force, fundamental force. So gravitational force, you will be thinking that what's responsible for that? There's a particle called graviton. It's a proposed particle. We have found all the 17 particles in LHC, but we have not found that particle. So it's a proposed particle. So maybe quantum gravity, what you will be researching about in the next few years. Then there came Higgs boson in 2013. It was discovered. It was proposed in 1960, but then it was discovered by Peter Higgs, and he also got a Nobel Prize for that. It's called God particle because it's responsible for the mass of every other quantum particle. So by quantum particle I mean every other small particle which make up the atoms. So like why proton is heavier than electron? Because Higgs boson create a Higgs field, and proton acts better. It interacts better with the Higgs field, so it is heavier. And electron doesn't interact better with the Higgs field, so it's lighter. That's how we can say that it imparts masses to the different particles. And that's all for today. That's for the standard model of particle physics. Comment down in the section below, and so that we can know and improve ourselves. Please hit the like button. Thank you, and don't forget to subscribe my channel.